Hi, welcome to an audio test session with APX. These videos provide worthwhile information for APX users and demonstrations on a range of audio measurement applications. In this session, Eric demonstrates how to make audio measurements on a stereo power amplifier.
Hello. Today I'm going to demonstrate using the APX 500 analyzer to run a series of audio measurements on a stereo power amplifier. I'll set up the signal path for the device we're testing and then set the references. I'll show each measurement with its properties and settings, and finally run the tests as an automated sequence and show the resulting report. This will show if the amplifier meets the specifications. I'll be using an APX 515 analyzer and APX 500 measurement software version 6. The device I'm testing is a small stereo power amplifier designed to deliver 75 watts into a 4 ohm load. These are the published specifications. Okay, let's take a quick look at the physical setup. In addition to the amplifier under test, I have 4 ohm load resistors wired in parallel with the analyzer. And we also recommend using a ground strap between the DUT, device under test, and the APX analyzer. If the amplifier you're testing is a Class D design, you'll also need an aux filter placed just before the analyzer inputs, as shown in this connection diagram. Now we'll set up the signal path. So the outputs are going to be set to balanced, to channel, and the inputs also balanced to channel. The high pass will be set to DC, and the low pass to ADC passband. The bandwidth to 90 kilohertz, and I'll use verified connections to make sure that we have a complete signal path. Okay, good. Now I'll set the watts reference to 4 ohms, the value of our load resistors. I'll use auto generator level to find the correct level for our measurements. The amplifier specification is less than 0.01% distortion, so I'm setting that as the regulation target. Looks like it can't regulate to 0.01%, so I'll try 0.05%. Okay, still not happy. How about 0.1%? There we go. It found the generator level and set it into the dBRG, or generator reference. So now we can set each measurement in our sequence to this level by using 0 dBRG. So it appears the specifications on this amplifier are a bit overstated. Well, we'll see what it can do. All right, our first measurement is DC offset. The DC level view provides a single value result, the DC voltage present at the output of each DUT channel. You can make a DC level measurement with no stimulus signal, or you can use the generator to provide a stimulus to investigate how an audio signal affects the DC level at the output of the DUT. We'll use the sine generator and set it for 0 dBRG. And the limits we'll set for 10 millivolts. 100 millivolts is good, and 10 millivolts would be excellent. The level and gain measurement provides single value meter measurements of the output levels. So again, we'll use the 0 dBRG generator level. The specified gain is 30 dB. The THD plus N shows the total harmonic distortion plus the noise. So at full power, 1% would be considered good, 0.01% would be excellent. So we're obviously going to fall somewhere in there. I'll set the generator level, and we'll set the limit here. The frequency response measurement uses a log chirp stimulus to measure the response of each channel plotted against frequency. I'll use the default start and stop frequencies, set our level, and then run the sweep. I'm going to use this data to create limits. So I'll select Edit Limits, and then import copy data, and then I'll select from graph measured 1, and the number of points will set to 30, apply it to the upper, and then we'll create an offset. So I'll add 1.5 dB, 1.5 dB, select OK. And we'll also set this one to the lower. So we'll create a new offset here, and this one will be minus 1.5 and minus 1.5. Click OK, save that new curve, and then click OK. And now we have some limit files created right from the data that we acquired from the DUT. Signal-to-noise ratio is a result of two measurement acquisitions, one at operating signal level and the other at an idle condition. The first being the signal and the second being the noise. So we'll set our generator level, and then the limit is set at 80 dB. We'll also add an A-weight filter to this measurement. The crosstalk one-channel undriven measurement provides a measurement of the crosstalk into one unstimulated DUT channel, the undriven channel, when the other channel is stimulated. This crosstalk measurement automatically steps the measurement through the channels to provide results for both channels. So minus 50 dB would be considered good, and minus 60 dB would be considered excellent. Inter-channel phase displays the relative phase of the DUT channels. One channel is chosen as the phase reference channel, and the remaining channel is measured against it. IMD, intermodulation distortion, gives a measure of distortion products not harmonically related to a pure sine signal. These artifacts can make music sound harsh. IMD measurements use two sine tones at different frequencies, summed into a stimulus signal. We provide a split function for acoustic summing when testing microphones. This measurement provides single-value meter results for IMD ratio and IMD distortion products. SMPTE IMD is a technique for measuring IMD standardized by the Society of Motion Picture and Television Engineers. The stimulus is a strong low-frequency interfering signal, F1, combined with a weaker high-frequency signal of interest. You set the ratio here. IMD less than 1% is considered excellent. In CMRR, or common mode rejection ratio. Common mode refers to a signal common on both the positive and negative sides of a balanced cable presented to a differential input. Common mode signals are typically spurious signals picked up from the environment common to both leads and should be rejected to a high degree by differential amplifier inputs. This measurement only works with the balanced analog outputs. 70 dB would be good, 90 dB would be excellent. Maximum output measurements use a sine wave stimulus signal that is adjusted to the level that produces the target distortion in a selected channel using regulation. This method is often employed to perform measurements at an amplifier's maximum output level. I'll set the target to 0.1% and let's see what the output is. Okay, we get the 75 watts claimed, however, at a higher distortion level than specified. Our last measurement will be the stepped level sweep, where we can plot total distortion and noise versus measured level or output power. I'll set the y-axis here to watts, and then define the right axis as THD plus N ratio. And here we can see as the level is increased, the distortion is reduced, the output power comes up until the point where we start clipping the amplifier where the distortion sharply rises back up. And then last but not least, in post-sequence steps, we have the report enabled, so it will be displayed at the end of our sequence of measurements. This concludes my stereo power amplifier audio measurement demonstration. Thanks for watching.
Thank you for joining us for this audio test session with APX. For additional videos, visit ap.com or any of our social media channels.